Today we have the lecture number 4 of the course, Application of Navier Stokes equation. Earlier in the past week we have done 3 lectures in which we have derived continuity equation and we have derived momentum equation. In this lecture we will talk about Navier Stokes equation, which is actually a combination of continuity equation as well as momentum equation, and we will see that these set of equations actually govern the fluid flow. So that's why we call such equations to be governing equations. And then we will have an application of the Navier Stokes equation for a problem in which we have a steady state situation and a laminar flow, and the flow is taking place between the 2 fixed plates which are infinitely long. So we will solve the Navier Stokes equation in this part, and then we will our solution to this Navier Stokes equation would be result into a profile, what we call it a velocity profile. From getting this velocity profile, after getting the velocity profile, we will be in a position to calculate so many things, including the volume flow rate, including the average velocity, including the maximum velocity, or we have information about the local velocity, and finally we will calculate the Reynolds number from that velocity profile. So this is the content of the lectures, today's lecture. Let's see, this is momentum equation in the vector form, and we have already derived here. It is in the vector form, means v is a velocity vector having component in x, y and z, and this is a material derivative. And if you recall the previous lecture, so this term is actually the inertial force per unit volume, and this is actually the density times acceleration is actually the body force per unit volume, which is in this case we have only included the gravitational force per unit volume. So this is the pressure force per unit volume, and this term is actually representing a pressure gradient, and the 4th term is about the viscous term. So all these 4 terms are actually, these are not one equation, but these are 3 sets of equations, and we call it momentum equations for each component of the velocity. In Cartesian coordinate system, if you expand this vector form, this is a vector form, if you expand this vector form in Cartesian coordinate systems, you have a density here out of the bracket. It means actually the properties of the fluid are assumed constant. The properties of the fluid includes the density of the fluid and the viscosity of the fluid. So these two things are no more changing with the time and space. Similarly, this mu is outside this bracket part. It means mu is no more changing as you are moving in x, y and z directions. This term, this initial term, this material derivative term, we have already learned that it has 2 components. One is the local variation of the velocity in x direction, plus this is the convective part. So there the velocity is changing in x, y and z directions as you are moving with the velocity vector having components u, v and w. So this is the x momentum equation, and these 2 terms are actually the inertial terms. So if you have a steady state problem, obviously the variation of velocity is not taking place with the time. Okay, the next term on the right hand side is the gravitational force per unit volume. This is the component of the acceleration vector in x direction. So this is the pressure gradient term, how the pressure varies in x, and you know negative is because of the sign convention that the pressure always acts inwards. And this is the viscous term, and this is a non-linear term because it's a 2nd order term of how the velocity change takes place with respect to the change in x square. So it's a 2nd order term. Similarly, we have momentum equations for y direction, and this is the momentum equation for z direction. And how to recognize it, because velocity in x direction is u, velocity in y direction is v, and velocity in z direction is w. So we will restrict this notation, we will restrict ourselves throughout the course to this notation. And then we have obviously while deriving this, we already use this continuity equations to simplify our momentum equations. So we have already learned in the previous lectures in the derivation that we have already employed this continuity equation into the momentum equation, so that we will be able to simplify it in this manner. So we have four unknowns, like u, v and w are unknowns, which are actually some functions of time and space variables. And the next unknown is the pressure. So pressure and 3, it means you have four unknowns. So you must have four equations in order to solve the set of problems. So the problem here is determinate, because you have four unknowns u, v and w, and pressure. So this is how we write the momentum equations and continuity equations. And once you show them together, it's a combination of three momentum equations and one continuity equations. If bunched together, it is actually termed as Navier Stokes equation. So Navier's equation is basically a combination of momentum equations and continuity equations. And we already have learned the continuity equation is based on the principle of conservation of mass, is a fundamental principle, while this momentum equations are derived based on the conservation of momentum principle. So Navier's equation is actually the coming out of the fundamental laws. So that actually governs the fluid flow. So that's why we call such equations to be governing equations of the fluid flow. In today's lecture, we will be solving these Navier's equations, and we have taken a simplest of the problem in which we have two fixed plates, and the distance between the plate is 2h, and for showing up, we have a b is the width of the plate in the z direction, and x is the direction parallel to the plate, y is the direction perpendicular to the x direction, and z is the direction which is out of this paper or out of the slide. So here acceleration is acting in the negative y directions. Okay, so this problem can be solved using applying the Navier's equation to this problem. So as we know, the Navier's equation is complicated, having nonlinear terms as well as variations taking place with time as well as space variables. So we have to take assumptions in order to solve this. Okay, here our first assumption here is a steady flow. So once we take in a steady flow, it means the parameter of interest, any parameter of interest, whether the velocity, whether the pressure, or any parameter doesn't change with the passage of time. So such problems are called steady state problems. So for example, whatever the velocity profile is this, it is no more changing as the time progresses. So at 10 o'clock, the velocity profile looks like the same. At 10:30, the velocity profile looks like the same. So it means that is actually called as steady state problems. Second assumption we have taken here is the flow, that fluid which is flowing between the two plates in such a manner that the streamlines, or actually we will talk about later about the streamlines, but fluid is flowing parallel to the plate. It means there is no component of velocity present in the y direction. Similarly, the fluid is not coming out of this in the z direction. So the velocity component in v and w, which is velocity component in y and velocity component in z, is taken to be 0. So the fluid is only flowing in the x direction. So the fluid is flowing between the two plates. So this is our second assumption. Third assumption is, which is actually not an assumption but a situation because g is a vector. G is acceleration due to gravity vector, and vector always the acceleration is always downward. So the acceleration in x direction would be considered as 0. Similarly, there is no acceleration taking place in z direction, so acceleration is only present in the y direction, and the magnitude of that acceleration is minus g. Minus is just because acceleration is acting downward and y direction is taken positive. So that's why we have a negative sign here. The fourth assumption here is since we have assumed that the velocity is varying in the x direction, I mean the dominant direction for the fluid flow is in x, so throughout x there is no variation taking place as far as the velocity component in x is concerned. There is no variation taking place in the z direction. So if we take small width b becomes infinity. It means b is very large. So we have very large, infinitely long plates, so the width b is approaching towards infinity. So it means whatever the section we cut here, the velocity profile remains the same. So we are not talking about what is happening at the edges of these infinitely width plate. So we are only bothered about dominantly what is happening in this z. We are not interested in what is happening in this z direction. So these are the four assumptions, and these four assumptions we are going to employ in order to solve our governing equations. And let's see how we apply here. So we have a problem at hand, the two fixed plates, and we have assumed the steady state. We have assumed laminar. It means the fluid is flowing parallel to the plate, and acceleration is always acting downward, and it is infinitely width plate, so that the variation of the velocity is not taking place in the z direction. So these are our four assumptions, and I have used some color coding here. The red is steady flow. It means the variation of time is not taken into an account, and the green one is about parallel flow, and the blue one is about acceleration terms, and this brown color is about the fourth assumption. And let's see. Okay, the step for solving such problem is because whatever the fluid flow is, we have a Cartesian coordinate system. So we have to write the governing equations first of all in the given coordinate system. So this problem is about Cartesian coordinate system. So what I do is I write down the governing equations in the Cartesian coordinate systems, and my governing equations includes the continuity equations and three momentum equations. So this is always the first step with respect to the problem. First work out what is the coordinate system, and write down the governing equations in terms of the coordinate system. You have already done an assignment where I have asked you to write down continuity and momentum equations in cylindrical coordinate system as well as a spherical coordinate system. So you just need to take the mathematics. For example, here the variables are x, y, z. So it could be r, theta, phi in cylindrical coordinate system, or it could be r, theta, phi in two angles which are in a spherical coordinate system. So in cylindrical coordinate systems you have r, theta and z. In spherical coordinates you will talk about r, theta and phi. So I mean we will see later about such different other coordinate systems. So right now we just focus on Cartesian coordinate system. So the first step in solving the problem is whatever the problem given to you, you have to write down the governing equations keeping in view the coordinate system. So right now we have Cartesian coordinate system. So this dimension is x, this dimension is y, and this dimension is z. So our first assumption is steady state. So we have to look for the terms where time is an independent variable. So time is independent variable here, here, here. Since the variation of any component of velocity, whether is in x, whether in y, or whether in z, is no more depending on time. So these terms would be, okay, so now you see the red color. Red color is about, because we are not interested in these terms would be 0 because our problem is steady state. So this term is gone, this term is gone, this term is gone. So in this inertial term of momentum equations, all these three terms are gone by employing the assumption of steady flow. The second assumption is the parallel flow. So parallel flow talks about that there is only the dominant direction of the velocity is in x. So u is the velocity component that is an active component, whereas since there is no flow taking place in the y direction because the fluid is not coming out of the plate, so v is 0. Similarly, so this b is so big that there is no flow coming out in the z direction. So we are assuming it that v and w are 0. So I have used the green color. So if you look at everywhere, when velocity v is there, which is 0, velocity w is 0, velocity v is 0, velocity w is 0, v is 0, v is 0, w is 0. So everywhere you have v and w 0. So what you end up with, lot of terms have gone by employing the assumption number 2, because we are only interested in the variation taking place in x. So velocity in y and velocity in z is 0. So that's why all these terms are gone. The next assumption is about acceleration due to gravity. So if you look here, acceleration in the x direction, because there is no acceleration due to gravity in x, there is no acceleration due to gravity in z, only acceleration due to gravity in the negative y direction. So that's why what we have to do is with the blue color, you look at here in the blue color, what you need is, because this velocity, because g is a velocity acceleration due to vector, acceleration vector, which has component in x, y and z. So the component in x and z would be 0. So only acting component would be the gy. Okay, so this term we cannot get rid of. Okay, the next is the variations that has been taking place of velocity component u, which is we cannot, here v is 0, but dava u by dava y is not 0. So we have no information about what the dava u by dava y. We have only information about that the multiplier v is 0. So if any multiplier is 0, whatever the gradient of the velocity in y direction, the term would be 0 eventually. So the next is when you are assuming it, the plates are of infinite width, so b is approaching towards infinity. It means that their velocity component u is no more changing in the z direction. So we have only this term is u changing in the z direction, because this term is already 0. So next term that 0 would be only this term, because this is the velocity variation taking place in the z direction. So you end up with so many terms cancels out. So what you eventually actually end up, and the next is you get rid of 2 more terms, because you know the velocity is no more changing in z, but velocity is changing in x, velocity is changing in x, velocity is changing in y. So here, as you know, these 2 v's and w's are 0. So if you employ this into a continuity equation, so your continuity equation would result in the velocity variation of u in x would be 0. So by employing this continuity equation, you end up with this term would be 0. U is not 0, but dava u by dava x is 0 from continuity equation. So that is our not an assumption, but we got, by employing the assumptions, we got a continuity equation in such a way that the velocity variation of the u component of the velocity in x comes out to be 0. So if this is 0, then obviously the second order term would also be of no importance. So eventually, once you apply all these assumptions, the red one is a steady state, the green one is, if you go back, is a parallel flow, and the blue one is acceleration, and the third one is the because of the infinite plates. And the gray one is eventually due to employing the results you got it after those assumptions you got it from continuity equation. So our continuity equation looks like simple. Only w by x would be present here. So that would be 0. So what this equation is suggesting, that the velocity component of x, which is u, so as you are moving in the x direction, it is not changing, and we will talk about it later what this is all about. So it means there is a variation of velocity takes place with respect to y or with respect to z. We don't know because it's a partial derivative, but we are sure that it is no more changing with x. Our first momentum equation, we call it equation 1 here, would have, there is no term because all the terms gone. So whatever the row is there, but if you multiply by the zeros, so you end up with a 0 here in the left hand side of the x momentum equation, and this term is 0. So only you end up with the pressure gradient term. And for the viscous part, you already gone with this variation in z because infinite plates, and this is an outcome of employing the continuity equation. So what you end up with, only this term. So this we call it equation number 1. What about this equation number 2, which is a y momentum equation? So all the initial term is 0. I mean, there is no active term, but the gravitational force that is present in y, so gy is taken to be minus g, so you end up with minus rho g, because gy is actually minus g. Minus g is because acceleration is acting downward, which is in the negative y direction. So you left with this term, and you end up with this term. Since velocities are 0 in y direction, velocity component in y direction is 0 because there is no flow which is coming out of the plates. So all the viscous terms of the y momentum equations are gone. So you only end up with the pressure term, you only end up with the gravitational force term. So that is, we call it equation number 2. And the third equation looks like, because the whole all these terms are gone, we've gone with this gravitational force term, we've gone with this viscous term. So you only end up with that the pressure is the varying with the z direction. So it means, and since the left hand side 0, so it means this would be also 0. If you divide by minus, it would be 0. So this equation is suggesting that the pressure is no more changing in the z direction. So these 4 equations we got it, these would be our governing equations. We got it from our Navier Stokes equation by employing the assumptions to the given problem. So this is how you have to look at these problems. First you have to write down the governing equation in a given coordinate system, and then you have to write down the assumptions, and then you have to cut those terms, and then you are in a position to simplify your equations. So if you look more closely these equations, so what we are interested in, because our variable of interest here is u or pressure. So these are the 2 variables which are our unknowns, and obviously they are changing with x, y and z, and let's see how we solve these set of equations. So from continuity equation, if you look back from our continuity equation, you got u by x is 0. So this is what I am writing down from continuity equation. So what this suggests, that the velocity component in x direction, which is u, is no more changing as you are proceeding in x direction. So for a given problem, you have velocity is varying, but velocity is not varying with x. So mathematically we can say that the velocity is a function of y and z. Is no more a function of x, because we know from coordinate equation that the velocity component is no more changing as x is changing. So we can say from this equation that we can conclude from this equation that velocity is a function of y and z. And if you look back, this assumption of velocity is no more varying in z because the parallel plates. So eventually you end up with velocity is only a function of y. So we know that velocity is changing with x, y and z, but from coordinate equation we learned that velocity is no more changing with x. So it is only from this equation we conclude that the velocity would be a function of y and z. And if we look at more closely from the parallel flow assumption that the velocity is no more changing with z, so the effect of z is not coming to this velocity. So eventually velocity in x direction would be some function of y. So this is, we have concluded from this mathematical results we got it by employing this thing and our assumptions. Okay, so the next thing we have to do is from equation 3 we learn that it's a partial derivative of pressure with respect to z. So once you write a partial derivative, it means pressure is a function of more than one variable. So it could be a function of x, it could be a function of y, it could be a function of z. But this equation is suggesting, equation 3 means momentum equation in z direction suggests that the pressure is no more changing in the z direction. So eventually exactly the same way what we have concluded for velocity component, we can conclude that since the pressure is no more changing with z, so pressure would be some function of x and y. So this is the conclusion we have drawn from third equation. If we look at the equation number 2, which is saying that the pressure variation takes place in the y direction, would be minus rho g. So it means if you pressure is some function of xy, because we already seen the pressure is some function of xy. So the pressure variation taking place with y equal to minus rho times g. So if you integrate this expression, so the change in pressure, if you integrate dp, it would be p, and multiplied because rho g is constant, rho is constant, so its integral would be y plus some constant of integration. So this constant of integration would be, since the pressure is varying with y, so it means the constant of integration would be some function of x and z, because we already know the pressure is no more changing with z, but the pressure is changing with respect to y. It means at this point we can conclude that this constant of integration would be some function of x and z, because pressure is only varying with y. But we already know that the pressure is no more changing with z, so we get rid of this z, because we know the pressure is no more a function of z. Therefore we can simplify this equation, that therefore the pressure would be minus rho g times v y plus some function of x, so it would be some constant of integration. From x momentum equation we know that the pressure gradient is mu times the viscous part, mu times the dou y square u over dou y square. At this place we know that this pressure gradient in x is equal to mu times the second order of the velocity with respect to y. So here we know, since velocity, we already have concluded that the velocity is a function of y. So velocity is changing as y is changing. So we can conclude that the velocity, as we know that the velocity is a function of y. So we can say here velocity is a function of only one variable. So we have converted this partial differential into ordinary differential. And we also know about, we haven't put anything on this pressure term, but we have changed the second order term from partial differentials into ordinary differential. The reason is the velocity is only a function of y. This is the final conclusion we have already drawn. So it means the velocity is a function of y. Okay, so you can write this term like this too, because just bringing this term onto the left hand side and everything on the right hand side, you have just brought it in the denominator. So this becomes your second order differential equation. So u is changing with respect to y. So how to get u? By integrating this expression. If you integrate this expression, the second order term would convert it into first order term by integration. And since this whole thing is varying with y, so y is here, plus some c1 is some constant of integration. Still the next step would be to integrate so that you have u as a function of y. So we have this expression, we further integrate. So it is y, then integral would be equal to y square upon 2. So because all this thing is assumed constant. So pressure gradient is taken constant, mu is constant, so u is only a function of y. So if you integrate this, the integral of y would be y square upon 2. So that's why 2 comes here. Plus c1 times y plus some constant of integration c2. Okay, as you know, we have got an expression for velocity profile which is some function of y. So if you substitute y, you will get the velocity component u. So c1 and c2 can be worked out because this is ordinary differential equation and you have solved this ordinary differential equation. So for this particular problem, you know the boundary condition is when y is 0, you have some velocity, but when y is plus h, your velocity is 0. Similarly, your velocity is 0 when you are at minus h. So this is because of the fact that the two plates are fixed, they are not moving, they are fixed. So the layers which is sticking, the layer of the fluid which is sticking to the both plates remains stationary. And we call such a boundary condition to be called as no slip boundary condition. So due to this no slip boundary condition, because the layer of the fluid which is in contact with the both plates, up top plate and the bottom plate, which is not moving. So velocity here is 0, velocity here is 0 when y is plus minus h. So what we do is one by one we substitute this boundary condition. We first put y equal to plus h. So substitute y equals to plus h here, and u is taken to be 0. So u is 0 and replacing y with h. So you got this equation, and then next you have to apply the second boundary condition when y equals to minus h. So when y equals to minus h, because minus h square would be plus h square, and here would be y would be minus h, so you got a minus c1h plus c2. So velocity is 0 when y is minus h, so velocity is 0. So you have two set of equations. So the next thing is to solve for these constants c1 and 2. So if you simultaneously solve, so you got the value of c1 0, you got the value of c2 equals to something like this. So what you need is to substitute c1 and c2 back into this equation to get your velocity profile. So we look like substituting back the c1 and c2. So eventually you got this equation because c1 is 0, so y term is gone. Only y square term is there and a constant term is there. So for constant term, you just substituted the constant term here. So here you know 1 upon 2 mu is a constant, dava p by dava x, which is the pressure gradient, is constant. So what you end up with only y square minus h squared. So you see velocity is a function of y, and if you substitute you got this result, and if you plot this equation, you end up with certain velocity profile where velocity is a function of y. The two plates are fixed, and here the velocity is 0, here the velocity is 0. And if you are putting different values of y, you are going to get different values of u. So these will be called as their local velocities. So whenever you solve any equation, you always need to check its boundary condition. Let's substitute y equals to h here. So if you substitute y equals to h here, h square minus h square would be 0. So whatever this term is, the velocity is 0. If you substitute y equals to minus h square, it would be h square. Minus h square would be 0. Once again, you got the velocity 0. So whatever your result is, whatever the solution of your equation is, you always need to check whether it is satisfying the boundary conditions. So if you check here, it is satisfying the boundary conditions, and we will see its velocity would be maximum, because this layer of the fluid would be moving with the maximum velocity, and these velocity layers would be retarded. And the physical reason is because there is a viscosity component present. So as you know, the magnitude of the velocity would be higher if the viscosity is lower, even if you are assuming the pressure gradient is constant. So pressure gradient in x is, if assumed is constant, so it means the velocity is increasing as mu is decreasing, if if the pressure gradient is constant. So the fluids which are highly viscous, so viscosity is low. Highly viscous means the velocity of viscosity is high. So when viscosity is high, so velocity would be low. So there would be an inverse relationship. And eventually you got this velocity profile. We see here this velocity profile. So variation of velocity, it is satisfying the boundary conditions, and we see the velocity become the function of y, and y varies from plus h to minus h according to our boundary condition. So this equation is suggesting, okay, how you can increase the velocity if mu is fixed. Either you change the position. If the position is fixed, let's say I am interested in the value of y to this distance, then only way to increase the velocity is to increase the pressure gradient. So more the pressure gradient, more will be the velocity. So between the two fixed fluids, if the fluid is moving, you want to accelerate the fluid or you want to increase the velocity, what you need is to provide the pressure gradient. More the pressure gradient, more will be the velocity. So if you look at how this equation relates and how you change the parameters that would affect onto the magnitude of the velocity in x direction. As you know, the volume flow rate is, if you see the variation of velocities taking place in the y direction. So if you take a differential element in y, that would be dy, so only a differential fluid element, and this is the volume flow rate if you multiply by their local velocity, because meter per second multiplied by meter, it would be meter square per second. Since we are talking in the z direction is 1 unit, so it would be 1 meter. So eventually the units of this equation would be meter cube per second, and meter cube per second means how many cubic meter flows per unit of time. So this would be your if you integrate, because y is varying from minus h to plus h, so the limit of this integral would be minus h to plus h, because u is varying in the direction of y. So you can calculate the volume flow rate by just substituting u here. So this would be your exercise for your home. Let's substitute u here. Everything is a function of y, assuming mu and dou p by dou x constant, integrate, you end up with some results. So I have just put up the results. So you have to check, if you substitute u here in this integral and integrate between the first integrate, then apply limits, eventually you end up with this equation. So your volume flow rate would be depending on the h, which is this distance, or the total width of the distance between the two fixed plates would be 2h. So you can increase volume flow rate, either you increase h because more volume would come into this, and or you increase the pressure gradient. So whenever you got certain results, you must be able to explain it in your own words. So you must be able to do the physical interpretation of the equations. As you know, a negative pressure gradient would result in the positive volume flow because the negative sign is here. So it means the pressure is changing in x direction would be negative. Means here you have a higher pressure at the upstream side, and the downstream side you have a low pressure. So higher pressure here on the upstream forces the fluid to move. So pressure here is low, pressure here is high. So the pressure gradient in x direction would be negative, and this negative and negative would make this volume flow rate positive. So if the pressure gradient is positive, it means the flow would be taking place from the downstream to the upstream. So here the reverse flow would take place when your pressure gradient is positive. So the negative pressure gradient is actually called, as we will learn later also, it is called as favorable pressure gradient, because this favors the fluid to move between the two fixed plates. Its maximum velocity we can easily work out, because just substitute y0. So I am just substituting y0 to get the maximum velocity, because y0, so your maximum velocity would be depending on h square, not h cube. So this is the difference you learn, because here y, when you put y0, so it will only end up with h square here. Similarly, we have learned that the local component of the velocity would be some function of y, and we know the velocity is, the question comes because between the two fixed plates, different layers would be moving with different velocities. So what we are interested in at that cross section, we will be interested in some representative velocity. We call that velocity to be an average velocity. So this average velocity is throughout the cross section, all the layers would be moving with the same velocity. So what would be that velocity? Because you know the velocity is varying in the y direction. So velocity is maximum when y is 0, and velocity is 0 when you are at plus h or when you are at minus h. So velocity is varying in the direction of y. This is the result we got it by solving our Navier Stokes equation or the governing equations of the fluid flow. So then how to work out this average velocity? So what we do is, there is some area under the curve of this velocity profile. So if you are assuming that this area under the curve is the same as the area under the curve of this uniform velocity, because the area under the curve of this rectangular bar would be u bar. We are assuming if we don't know what is that u bar, but if you multiply by this 2h, you will be able to get this volume flow rate. So let's assume that u bar is that average velocity. So this would be the volume flow rate. So area under the area of this rectangular strip, because this dimension is u bar, we don't know where it is, but this dimension we know it is 2h, so that would be equal to how the velocity is varying in the direction of y. If you integrate it from minus h to h, that would be the area under the curve, and these two would be equal. So this equation is nothing, just making sure that different layers would be moving with different speed. So the layer which is at y0 is moving at a maximum speed, and other layers are retarding. They are moving with some slow speed due to the viscous effect, and the layer which is in direct contact with the fixed plate is moving with zero speed because it is stationary. It is in direct contact with the stationary plate. So velocity variation is taking place. Velocity variation taking place in y. So this is actually the balance of the mass that has been taking place. And if you just integrate this, we already have done it by integrating this in the volume flow rate term. So you just substitute the result, and then you need to simplify this equation. U bar is, I have just multiply and divide by the same number so that I get 1 upon 2 mu like term. So eventually we can say that your average velocity would be 2 upon 3 times of this factor. As we already know, when y is 0, minus h square, this term is actually called as maximum velocity. So we have a relationship between average velocity and maximum velocity. So this is a maximum velocity. So this length, which is an average velocity, would be 2/3 of this maximum velocity. So if you know the maximum velocity, you can work out the average velocity, which is 2/3 times of that maximum velocity. Or vice versa, if you know the average velocity, you can calculate the maximum velocity, because the maximum velocity will be 3/2 times of the average velocity. Once you have done this, you have a knowledge of a velocity profile. You can work out maximum velocity, you can work out average velocity, and the last thing is the Reynolds number. You have already learned in the FM1 course, the Reynolds number is a parameter which is actually a ratio of inertial force and the viscous force. So rho u is an inertial force, rho ul, and mu is a viscous part. So we will derive later this expression in the later part of the course when we will talk about the boundary layer theory. But right now it is just to remember it is density times the average velocity times the characteristic length and the viscosity, which is actually a dynamic viscosity. And you know, kinematic viscosity is if you divide dynamic viscosity by density, you will be able to get kinematic. If you bring density down, you can write UL over nu. Nu is the kinematic viscosity. Okay, density is constant here, and we have an expression for average velocity. We know mu is constant, so only thing you have to substitute the what is the characteristic length. So in this problem, our characteristic length is the width of the plate, or the distance between the two fixed plates, which is 2h. So this is how you calculate Reynolds number. As you know from your FM1 course, Reynolds number signifies whether flow is laminar or turbulent. For example, in a pipe flow problem, you know 2000 or 2300 is a number. If it is greater than less than 2000 Reynolds number, it would be laminar. Otherwise, it would be transition and then turbulent. Here we will the Reynolds number, which is laminar case, because our assumption is laminar here. So if you calculate the Reynolds number by putting the density and average velocity and the distance between the plate and the viscosity, if this number is less than 1400, we will assume it laminar. Otherwise, it would be turbulent or becoming a turbulent. So far we have solved a governing equation using Navier. We have solved the governing equation for a particular problem of steady laminar flow taking place between the two fixed plates, and we end up with the velocity profile. And when the Reynolds number is greater than 1400, obviously the flow becomes turbulent, and our assumption of steady and laminar would no more be applicable, and we have assumed it a 2D flow, and this is in turbulent flows are not 2D, they are 3D, they are much more complex. So this is how we have completed our today's lecture.